No. I can't. She cannot come in. Sorry, didn't work out. Hello.
Hi.
All right. This one's real quick, so it's not going to take you any time. But that's okay. You guys can hang out a little bit. Everybody see? Let's take this up to maybe 200. Let's take a look at 200. Yeah, it's probably better. This one is actually quick. Good morning. You guys already done? "24 students. I'm almost done grading all the chapter 11s. I'm in the middle of, I'm halfway through my period 6. I've already done period 1, 4, and 5. There's also more retake / makeup. I have to do that again somehow. Maybe next week. I'll have to plan it either this week or in the weekend. I still have all the retakes to grade from before we went on spring break. So that was, I left those for last. Yep.
I'm eating breakfast in mommy's office.
Okay.
So I need this chair.
Go for it. You got it?
Yeah.
Okay. Good job.
Got it, Jack?
Jack says good morning.
Good morning to him.
That was cute.
Yeah, it's cute. And then, you know, there's all the other stuff. It's cute for a while, and then it becomes cute again. And then it becomes not cute again. We're going to throw in some secants today.
Mr. Rosenthal, for the triangles, are the vertex are both of those vertexes in the center point? Because it doesn't say and it doesn't look like it is.
No, not necessarily.
Okay.
Oh crap, Mom made it.
Are the two triangles similar or anything like that?
No.
They have a similar arc. I mean, they have the same arc.
Hold on 1 second. Oh. They do. Jack, Jack, attack. Yeah, exactly. Oh, Sam. So I just say here, show my work. I have my. Okay. You sent a message? I responded all day yesterday to messages. How could I not? That maybe you sent it and that was the after my last time looking at it. I don't know. I didn't respond. Send me another message, Sam. And I mean, right after I'm done with my 11 o'clock, I have office hours. And then after that, I go to the computer and I start answering messages. So leave me another message and I will get to it. Oh, that reminds me. There were a handful of people who I told them I could not see their revisions. For some of them now I can. There's a little arrow for revisions that allows me to look through the different revisions. So those that I said would have to retake tests, but now I know how to find the revisions. I'm gonna go in, it's gonna take me time to find all those for chapter 10 that happened to. You may not need to retake it if I can locate your revisions, if that was your particular issue. You guys got that?
Yeet.
Wait, what? There were a couple students who submitted their tests, chapter 10, 11, or both, with revisions. And I said, I can't see the revisions. I can only see the last one submitted. And so I told them they'll have to retake the test. For just that small group of students, it looks like I know how to look at the revisions now. So if I can see them, for that small group of students who that applies to, I might be able to grade those so that they don't have to retake it. So that would be good news for those students. Oh, we're past time. Nobody said anything. Okay. Good morning. Let's get moving. So this angle is inscribed and it has this arc, which this angle, inscribed angle, also has the same arc. And yesterday we said that if two inscribed angles share the same arc, they are what?
They have the same angle.
So it's 38, just like that one. They're both 38. So you could have been on this a long time trying to fit, well, we don't know if that's a diameter and we don't know if there's a center where that is. How would you do it? You know, so it was just really quick if you applied the theorem that these inscribed angles share the same arc. So I don't need to know what anything else is. I automatically know they're both 38. Questions about that?
That means that both triangles are actually congruent.
Uh-huh. Yes, they are. It means they're similar.
Oh yeah, yeah.
But I was right when I said that they were similar.
Uh-huh. But it's not given that they are. All right, I got to shrink this down. I really enjoy this idea because this next idea, there's a connection to calculus or pre-calculus in a way. Okay, I got to make this small enough. I think that maybe come back to 140. Okay, in the diagram, B and C are fixed points. They're not going to move. B and C are fixed points. All right. And point A moves along the circle. That's okay. So here's A, B, C. Let's look at this one first. I know it's really busy, the screen, but these are primes. It looks like B is going to move. Okay, so let's take a look. I think that from the inscribed angle theorem, you know that as A moves, the measure of angle A remains the same. I think that they're talking about B. So I'm not going to go off of this. The drawing is not matching what the words are saying. So you're just going to get confused. Everybody look at this first circle. Now I'm actually going to blow it up a little bit bigger because I can, because we're not paying attention to the words. Well, I can go bigger than that. Let's go 185. There we go. All right. Everybody focus on this first one here. This is A, B, C. Let's fix A and C, okay? Those will stay where they are, okay? Look at B. It's an inscribed angle. If I keep A and C the same, then this arc right here is going to stay fixed. And if I move B along the circle, the angle has to do what?
Stay the same.
It has to stay the same because it's going to continue to intercept the same arc. So everybody look at the second position, B prime. I have now slid from here down, and we know, whether I go through the center or not, that this arc did not change. So that angle has to be congruent to that first position. Now let's slide it even further. Where am I sliding it to, by the way? Where do you think I'm sliding it to? Well, you can see.
The tangent position.
Yeah, it's going to slide till it hits point C. All right? So, but when it hits point C, it's no longer inscribed. So what I'm doing is what we do in pre-calc. When you cannot, once I hit that, I'm not applying it to an inscribed angle anymore. And we might think that, okay, now we can't use the theorem to say if two inscribed angles share the same arc, then they are congruent. That's going to be a problem. But this idea that how is this behaving as we approach infinitely close to a point? As we approach infinitely close to a point, what is happening? And that kind of behavior can tell us what happens actually at, what it would be at the point. Give me 1 sec, I gotta close the window. Okay, so what happens as B is getting closer and closer to C, B is getting closer and closer to C, what's not changing is the measure of the angle. So when you actually get to C, it's like taking what we call the limit. The limit as this B approaches, I guess you would say radially approaches. I don't know how you would say that, because it's approaching in a circular path, not in a straight path. Okay, but as that's approaching point C, the angle stays constant. So what we can say that when it hits C, that angle that's formed is still the congruent to all the other angles, which are what? What's the relationship from yesterday we learned? What's
Half the central angle.
It's half the intercepted arc, right? Which is the same as the central angle. But right here, we're not showing a central angle. So let's keep the relationship between the angle and the arc. Okay, so the relationship here is that this angle is half the intercepted arc. So then this angle is also going to be half the measure of the intercepted arc. So what? But what are we looking at there? This could be a line that touches the circle in two places, called a what?
Secant.
Chord.
Tangent. Oh, see.
It's a chord.
A secant, it is a chord or a secant line, right, to the circle, intersecting a tangent line at the point of tangency there. We can now know something about that angle because of what we learned here and the sliding.
Half the arc.
That angle we now know is half this arc. So we can now discover things when tangents and secants start to interact on a circle.
Wait, Mr. Rosenthal, how do we know that?
I'm telling you, as this approaches, what stays constant is the angle. And as it infinitely approaches, all right? So it's as you infinitely approach, it fulfills that limit. It has to stay the same the whole time. It stays constant. What we're saying is the distance radially along the circle no matter how close you get to C, even if you're 0 away from C, right? The distance from C along this path doesn't matter. That's what we're saying. Once we see that the distance from C doesn't matter, then we know that the angle stays constant along that path. So once the B prime, B double prime, once you get here, when B is sitting right on C, it doesn't matter. The angle has to stay the same. Okay? That's how we know. All right. So here's the theorem, 1210. The measure of an angle formed by a tangent and a chord is half the measure of the intercepted arc. Okay? Be careful. There's this angle, and then there's this angle. It's this inside angle here, not the exterior angle. Okay? It's this interior angle here, is half of this arc. Okay, so if this arc is 60 degrees, this angle is 30 degrees. Any questions about that?
So how would we determine the angle of the actual arc?
One of them would have to be given in a problem, or there would have to be a way to know one so that you could get the other. You'll see when we have application. And I need to shrink this down a little bit. We're a little bit big here. Let's go to 165. There we go. All right, go ahead and try that here. So there's K down there. It doesn't quite fit, so, but you know K is down here. Okay, go ahead and try to do that problem. Find the measures of X and Y. And I'm going to start drawing it. Assume that that does go through the center, so that's a diameter. Let's say that that's a point of tangency. All right. All right, so what did we find out here? What did we find out? Anybody?
You know that the angle of J is a right angle because it is it's,
Technically don't know that yet.
Yes, you
Yes,
do.
you know.
J is inscribed in a semicircle.
Oh,
That's that big key theorem or corollary that I wanted you guys to have. Okay, I said assume this is a diameter. That means that angle must be 90 degrees. Now you can find what?
X.
You can find Y right now.
And you can also find X.
Well, do you know what this is here?
55.
Well, we can find X now right away, right?
Yeah.
Okay, but right now we have two angles in the triangle. I was going to stick with this triangle here. You know what this is, right? Because these two have to be complementary because you have a 90 degrees there. You have 90 left. So this would be 55 right here. Okay. Now we can look at this angle here as the inscribed angle, okay, for this arc. So these go together, okay? So this angle's 35. So what's this arc?
35.
No, it's double the angle,
Oh, right.
okay? So then this angle here that's made out of the tangent and this chord, that angle has to be half of that. Okay, so we know that that angle is going to match the inscribed angle. They're going to be the same. And imagine that I move point Q closer and closer, right? To where that became point Q. You could think of it that way. Or maybe that would be weird because then I would be crossing, but it would still work. to where
And
this would be QK right there.
how did you find x again?
I found X because X is this angle here. How is that angle formed? It's formed from the tangent, right? And this chord, right?
Right.
This chord has this arc, right? So we showed in the last slide that this angle was going to be half this arc. But that arc is related to that inscribed angle. That inscribed angle
Oh,
intercepts that.
okay.
So they're both going to be the same. These will both be 35.
That's what I was confused on. Okay, thank you.
Both of these are going to
Mr. Rosenthal, could you say that again? The
both
whole
of these
thing, I didn't
angles
quite
here
catch
are
that.
gonna be- yeah, I'm saying it. Both of these angles here are going to be half of this arc here.
Why would X be half of the arc?
Because X is congruent to angle Q because in the last slide we moved it
That goes
and
to theorem
it
1210.
was to the
1210 says that if a chord and a tangent line, right, form an angle at that point of tangency, then that angle is half the intercepted arc. And we showed it with getting infinitely closer with an inscribed angle, moving that point closer to one.
Oh, I see. Never mind.
Right? So it's the same as an inscribed angle. You're going to look at this angle as the same as an inscribed angle. That's how you're looking at it. So when you see that here in this problem, when you see the tangent and a chord meet, you're going to think of that as an inscribed angle who have these 2 points on the circle. And so it's related to that arc. Okay? So to simplify the situation, let's just make a simple drawing. If I have a chord, right, and then a tangent comes through there, if I think of this angle here as an inscribed angle, where is the arc that it's intercepting? It's going to be based on this point and that point. So it's going to be this arc. This arc goes with that angle. This is like an inscribed angle, same relationship. It's half the arc. Okay, so up here, angle X is doing that. So this arc here and angle X are related that way. Okay, any questions about that? No? Okay.
So JL we know is 30. Sorry, it's double 35 because what again? I'm just a little lost.
Okay, so going back to yesterday.
inscribed angle is half of the measure of the intercepted arc.
Right, I understand that. I'm confused on how you got the length of the intercepted arc.
Okay, hold on 1 second. So if this is 35 degrees, what's this arc here?
Double that.
Right. Okay. Now, let me move that over a little bit. So this is 70 degrees here, right? Now, what if I have a tangent here? Did that arc change, or is it still
No.
70 degrees?
The arc is still
If
70
I draw a
degrees.
chord, then this angle here is also half of the 70,
Okay.
right?
Yeah.
Okay. Or, if this was something else over here, then we'd be talking about this one with this chord, which is what we're doing here. This arc goes with this angle. It's just going the other direction.
Oh, okay.
Yeah, it's this one 35. So this arc is 70. So this angle is half of that.
Oh, okay. I see it now. Thank you.
Good. Yeah, and we just have to keep reiterating and you'll see it. It's just a matter of, being able to see how they're related. Anybody else questions or need to see anything again before we move on? No? Okay. All right, let's go forward. There's your homework. And just record that so that I can put that in right away. Page 558. 1 through 17, all. Geo. I'm putting it on a little board so I'll remember to put that on right away. I won't have that posted probably till, well, I'll try to do it right after the lesson, after office hours. Okay, everybody get the homework that goes with this? Okay, we're done with 12.4. We are almost done, folks, with our whole course. But we still have some challenges ahead of us, so we're not done yet.
Wait, how many chapters are there?
12. And we're
So,
on.
Mr. Rosenthal, thinking about it, I understand that like last year you had to do you had to waste a lot of time on preparation for the SBAC. Since we won't have that, will we not be in as much of a rush?
We haven't been. I don't know if you guys even noticed, we've only gone an hour a day, but we're doing more lessons. So we are covering a lot of stuff, but we're not going at a very fast pace. I'm kind of going slowly. I'm giving you guys extra problems that weren't in the curriculum. Like the Paul Bunyan problem was not in there. I'm taking time to talk about, the sciences and stuff like that because I'm not in a rush. So you guys feel free to slow me down, ask more questions about what we're talking about here.
So wait, we had time for Johnny's philosophy questions?
Who's Johnny?
Do you not remember Johnny from our class?
Jonathan?
Yeah.
I've never heard him called Johnny.
Oh, yeah, everyone calls him Johnny.
As long as they're related, I don't want to go off.
I don't.
Yeah, I don't want to go off topic. I want to keep it related to what we're talking about. Okay, so let's do these true or false questions here one at a time. So let's do number 1. All right. If two angles inscribed in a circle are congruent, then they intercept the same arc.
False.
False.
Is that sometimes true?
Yes.
Okay, what's the convincing argument that it could be false?
You can have two congruent arcs with two congruent inscribed angles.
So this arc here could be congruent to this arc over here. Okay, and so you can have that angle there and that angle, they would be congruent, those angles, but they would not intercept the same arc, they would intercept congruent arcs. Okay, so they don't have to intercept the same arc, they can intercept congruent arcs. Any questions about that? So if these are congruent, and they don't have to be the exact same arc. Okay, next one. If an inscribed angle is a right angle, then it must be inscribed in a semicircle. What do you guys think about that claim? If an inscribed angle is a right angle. So let's do that.
True.
We have to, okay, so let's make this, we'll come down to here, and then we'll make it a right angle. Of course,
Doesn't that look like a center?
nope, it doesn't, but is it true that that must be a semicircle then? Is there a way to have a counterexample? Nobody's saying anything.
No. You can prove it by saying, oh, if it's an inscribed thing, if it's an inscribed angle, that's a right angle, so then it has a 90-degree measure.
So what's this arc here?
180 degrees, and that's the definition.
If that's
of a
90, then by the theorem, this has to be 180. And then that defines a semicircle. That's the definition. An arc with a measure of 180 is a semicircle. So that must be the case that if you have a right angle, inscribed angle, that has to be a semicircle. There's no choice. You have no choice. Question, if we move on to Algebra 2, will I have days off? No. Going to school is not about finishing the curriculum. You're missing the point of the whole thing about education. It's about keeping your mind going. It's not about getting to some destination. It's really about the journey, the thought process, and the growth. Okay, so it's not about, we are going at a pace where you guys can take as much time to get these concepts. I'm not in a rush. The pace could be going fast for some and not for others. That's all subjective. If we're moving fast for some, that's not my intention. It's just when I say this is the idea, any questions, no questions, we move on. That's what's setting the pace, not me saying, oh, it doesn't matter what the question is, we're time's about to be over and we need to move forward. You're not going to hear me say that. Okay, if you do, let me know. Okay, so that being said, when we get to Algebra 2, we're going to take our time, but we're not going to have days off, because for 1 hour a day, you get to contemplate mathematics. You know, that's not asking a lot. It's not that I'm asking, it's not even me asking you to do this. It's really something that you need to be doing, and I'm hoping that you want to do it. You're quarantined, you know, you're stuck inside. You know, mathematical thinking is a specific type of thinking that it's good for your brain to do daily, like exercise. Okay, enough of that. All right, this is the hardest case. I wonder if anybody could prove this next thing. A circle can always be circumscribed about a quadrilateral whose opposite angles are supplementary.
True.
You think so?
Yep.
I would say so.
How can you prove that?
Because the opposite angles are supplementary. That means, let's start with the opposite angles are 90 degrees. If that's 90 degrees each. If that's true, then they make two semicircles joined as a circle.
But that's only in that special case.
Yes, I know. But if we tilt it, it'll still be the same thing.
Why?
You can tilt it and then.
So let me read this again. If these are supplementary, see how that's y and that's 180 minus y, that makes them supplementary? And same with these. Does this have to be cyclic, meaning fit inside of a circle, be inscribed in a circle? Is there a way to make a circle that doesn't circumscribe this? If this is the case, if these are supplementary, does it have to be the case that it fits in a circle? All 4 points, all 4 vertices.
No.
So, I mean, it seems like that would be the case, but maybe some people are thinking, well, is there some way that there's a circle that does that, or maybe a circle that does like that? Maybe I can draw the quadrilateral in a way that it does that. So maybe I can start with the circle instead of the quadrilateral. Is there some quadrilateral that either does that, and these are supplementary and those are supplementary?
Mr. Rosenthal, don't they say that in a cyclic quadrilateral, all opposite angles are supplementary, so you can just use the converse of that as a proof?
We don't have the converse of that. We don't have a theorem that says the converse of that. I'm drawing you 2 different quadrilaterals that are not cyclic. Let's say that we're given that these are supplementary. Is this inner one or the outer one possible? Those would be counterexamples. If I give you that these are supplementary and that these are supplementary, is this scenario possible? That's what I'm asking you to contemplate. Okay, let's start with the outer one. This is going to be an indirect proof. All right, so you're given that X and Y, and let's call this A and B.
Yes, I think
are supplementary.
I have a thing.
Okay.
So you have a quadrilateral, and its angles are supplementary.
X and Y are supplementary. X and Y are supplementary, and A and B are supplementary.
The the circle's whole measure is 360 degrees.
That's right.
Your two vertices. This is to prove that it works, by the way. Your two vertices, each are half of the arc opposite, right? And those two arcs will add up to the whole circle. Half of 360 is 180.
Wait, start over. Say that again.
Okay. If your opposite vertices are supplementary, they're both inscribed angles. And they both intercept an arc.
X is an inscribed angle. Okay?
Yeah.
B
Yeah.
is inscribed up to that point and this point. A is inscribed to there, but not there.
No, it's not. It's not to say that it doesn't work. It's to say that it works.
We're trying to see if it always works. We're not trying to see if it works in one case.
Yeah. All right, let me just do this. Okay,
It always works.
hold on one second. Let's say that this is given, supplementary. Opposite angles are supplementary. And let's assume that it's not cyclic. So in case one, there's two ways for it to not be cyclic. Either that fourth point is outside or it's inside. So let's do this first case where it's outside. That means that there is some point, let's say right there, that's touching it, forming this secant that is, and so now it is cyclic. Now we can use the theorem because this one now is cyclic. So now let's call this point Z or angle Z, right? Angle Z in this quadrilateral would be what with angle X?
Supplementary.
So X and Z are supplementary.
Z and Y have to be equivalent.
And X and Y are supplementary. So if two angles are supplementary to the same angle, then by the congruent supplements theorem, Z and Y would have to be congruent.
And since Z is an inscribed angle, Y would also have to be
Hold on, let's not get ahead. These have to be congruent. However, take a look at this triangle here. Z is what kind of angle compared to this?
Exterior.
It's exterior. So it's equal to the sum of this one and that one, right? So if Z, let's call this angle here W. If Z is equal to W plus Y, then by the comparison property, Z must be greater than any one of these alone. Z has to be greater than Y, which contradicts.
Because W can't be Z.
So it cannot be the case. Therefore, our first assumption that this is not cyclic and outside the circle must be false. So now the only other case we can look at is if this point is inside the circle. You see how useful the indirect proofs are so useful. So let's do this again.
The inside the circle is the same strategy.
It's the same, yeah. So
Yeah.
see, I'm taking my time with this, and it's not, this is just bonus. Okay, so let's say that you have a quadrilateral, okay? And the fourth point here is inside, okay? And so we have X and Y, and we have A and B, supplementary, opposite one supplementary. What you would do is you would do the same thing, and I'm not going to go through the whole thing again, but you can just, postulate 1, 1 through 2 points. There is one line, right? So you would get this other point out there, and then you can connect this.
But that would change angle A. It would
Hold on.
no longer be supplementary.
It doesn't change X though,
It
okay?
changes angle A. They're not supplementary.
But, okay, so now you have Z out here, and this quadrilateral is now cyclic, which means that X and Z are supplementary, right? So now you get the same thing, that Y and Z are congruent because of the congruent supplements
And
theorem.
the exterior angle.
Okay, and then Y is an exterior angle. Y is equal to W plus Z again. All right, and so Y has to be greater than Z, but that's a contradiction. Okay, so if it's impossible, then we just showed it with an indirect proof that it would be impossible to have a quadrilateral with both sets of opposite sides supplementary and for it to not be cyclic. So there's your converse, even though the curriculum is not asking you to prove a converse, we're doing the converse. So that would work. So hopefully that helps develop that understanding of the cyclic quadrilateral.
Here's another thing that you could do.
What's that?
So let's assume that it is cyclic. If so, x and y are both inscribed angles, and they both have each of their intercepted arcs, and neither of them overlap the other. Okay. Therefore, they must add up to the whole circle, 360. And if they add up to the circle and they must be half of the central angle, then you divide by 2 because they're half of the central angle, and you get 180, which means they must be supplementary.
Even if they're not the same.
Yeah.
But I think that is still the forward theorem. That's not the converse.
What's the forward theorem?
The first theorem that said that if they are cyclic, then they must be supplementary, which is what the way that your logic flowed. It went in a certain direction. Okay. All right. So here's a little activity for you guys to see how much you're getting of this. So we're FE and FD are tangents. So I want to see if you can find all these things. Let me shrink this down a little bit more. Can you guys see it? Maybe I'll leave it and then I'll get you the last one in it. There's let's see, number 6 down here is CE. Okay, go ahead. Number 6 is CE. Okay, and I'm going to draw that while you guys are doing it.
Do we know the center of the circle is point C?
Yes. Assume that point C is the center.
Mr. Rosenthal is the third one, EBD.
Yes, EBD.
Thank you.
You got it. Oh, this is the length too. This is definitely not drawn to scale. 4. That 2 looks bigger than the 4, certainly not half of it, but just, you got to go with the labeling. All right, so that's everything given. Number 6, you can't see it's here, so I put it here. You're trying to find the length of CE. These are FD and FE are tangents. All right, so let's find the measure of arc DE. This arc here should be the same as the central angle. This arc is 57 degrees.
In what cases is it the same as the central angle? And in what cases is it twice the central angle?
It's never twice the central angle. It's twice the inscribed angle. But it's the same as the central angle. So if I had a point from B, if I drew that to E and D from here, that would be half of the 57.
Okay, thank you.
Okay, let's look at the measure of arc AED. Oh, well, arc AED is a semicircle.
Why do we have a semicircle, but the bigger part is labeled 57?
Yeah, I was going to ask about that.
Because I said it's not drawn to scale.
There you go, David.
So 180 degrees is the second one. Let's see. Number 3, the measure of arc EBD. Oh, so that tells you the order. It has to go this way. I need that arc. Oh, well, the purple part is 57. So 360 minus 57, which is 303. Oh, no, EBD is 303 degrees, right? The blue is 303? Because it has to add up to 360 with the 57.
Wait, how come if it's not the full circle?
It is.
Oh, it is. It is.
Blue, follow it. Blue goes all the way around to here. And then this 57 is the purple part.
Okay.
Okay, now on to angles. Angle EAD. EAD. This angle here oh, I didn't draw I forgot to draw that segment. So we want this angle here. Well, that angle is inscribed. So follow the angle. It's the purple arc. And it's half of that. So that angle is going to be what? 28.5 degrees. The next one is angle AEC. Angle AEC. AEC. Okay, so this angle. Well, how would you get that one?
Angle ACE is supplementary to angle DCE. So then you could find that, and then you and then say that
Well,
that all the angles in a triangle add up to 180 degrees.
Well, can't you use the triangle exterior angles theorem?
Oh yeah, you can also do that.
Okay, or
and you can also do
Yeah.
Isosceles triangle.
Yeah, because these are both radii here, from C to E and C to
That's what I
A.
use.
So this is isosceles, yes, here and here. So then the base angles are the same, so 28.5. Okay, I like these little puzzles. These are good. Okay, and then on to number 6, which is here, the length of CE. Well, it looks like the radius is 4, so it's always 4. This is 4, this is 4. They're all 4, they're all radii. Let's see, what color has not had a chance here? They've all had a chance. So let's go to DF. Okay, what's the length of that one? How are we going to get the length of DF?
I think this has to
Congruent.
do with like the circumscribed
Congruent to
quadrilateral.
EF because the tangent something it was
We had a theorem, yes, we had a theorem that said 2 tangents that meet outside the circle must be equidistant from the point their points of tangencies, right? So this has to be 2 to match the other 2. So we're bringing everything back in, folks. So this is like review for you. This one problem is giving you a review of all these theorems that we talked about. So you should know that from a point outside the circle drawn to 2 points of tangency, that distance has to be the same. What about CF? What's that distance?
Okay, what?
We're at 20.
Yeah, 5√2.
Okay, so how do you know?
The triangle.
Give me what you're.
Pythagorean theorem.
Why can you use the Pythagorean
Equal
theorem?
to fourth word. It's right angle, tangent.
So okay, so A little bit more.
Why is it 5 root 2? Isn't it 2
Tangents
root
are
5?
tangents are perpendicular to the radii.
Okay, so you
Yeah,
have a
right.
radius drawn to a point of tangency. So this is a right angle. And over here, you have the same, a radius drawn, right? So either way, you have these right triangles. A 2 and a 4 are the legs with the hypotenuse here. Okay, so it's 4 squared plus 2 squared, and then the square root of that is going to give you CF. So 16 and 4 is rad 20, which is
5 rad 2.
No, 2 rad 5.
rad 5.
All right.
Same thing, right? No.
Yeah, definitely.
Yeah. Okay, last one. The measure of angle EFD. This angle here. What is this angle going to be?
123.
123.
Ah,
because
okay.
quadrilateral.
How do you know?
Minus 2 right angles, that's 180. Minus 57, that's 120.
Okay,
Supplementary.
but tell us what you're looking at before you're doing the
There's a
calculation.
quadrilateral CEFD.
This quadrilateral here has 360 degrees in it. 2 of them are already taken up, 90. So 90 and 90, 180, leaving you 180 between these two. This is a theorem we're about to have in this section, I believe, or late coming soon. It says something about this point and this central angle.
Yeah, coming soon.
They're supplementary. These angles must be supplementary. So that's the quick. Now you can know in the future when you get this scenario, 2 tangents meeting at the center here, these 2 angles formed are supplementary. So this has to be 123. So that the 57 and the 123 add up to 180, the 90 and the 90 add up to 180. Questions about that?
Wait, Mr. Rosenthal, how is AEC also 28.5?
Well, aren't these both radii?
It's isosceles base angle
This
theorem.
makes this triangle here, AEC triangle, isosceles here. So that means the base angles have to be congruent.
Oh, okay.
The exterior angle is 57 degrees, meaning the 57 must be the base angles added.
Yes, that's another way to look at it. All right, so we went through these 9 problems that helped spin you back through the different theorems that get applied to solve these things. So, you know, you're going to have some test questions. They're not going to be one drawing with 9 of them, but you might on the test get a drawing like this with 3 questions where you're going to have to find out one to get the next, going through the different theorems. So the way that you're going to be tested is like that, where do I know how these things are related? So make sure you go back over this, study how these things, this is a great problem to review before the test.
Is this the chapter review, Mr. Rosenthal?
No, this is the warm up for 12. Well, why does it say 12.4? I guess this is 12.4.
Understood.
Warm up for 12.4. Okay? This is the warm up for 12.
Wasn't the last one 12-4?
Understood.
I thought it was. I don't know what's going on. Now
I could have sworn that we've
It
done
was
4 lessons.
12-3.
The last one was 12.3.
Last one was 12.3.
Yeah, the
Okay.
last was 12.3. Yeah. So this is 12.4. Must be. Okay, so moving along. We're not going to be able to go too much further, but let's keep going. Okay, secant. We've already told you what that is. I kind of spilled the beans, I guess, earlier about secant line. This is where they actually bring it in that older book. Okay, so the secant is a line that intersects a circle at 2 points, not 1. You can have a ray AB be a secant. So imagine that's an endpoint. And then you just go in one direction. That's a secant ray. You can have a secant segment, right? A to B. If A and B were on the circle, it would be a chord, right? All right. And you can, of course, have a secant line. Angles formed by secants, tangents, and chords, they intercept arcs on circles. So you have this arc here, and then you have this major arc here. Okay? And that's because it's touching 2 points. The measures of the intercepted arcs can help you find the measures of certain angles. That's what we're going to get into. And we're going to have to prove what we say. And that's where the challenge is going to come in. Okay?
That was the best sound in the background.
What is wrong with your children?
They, at the moment, are fighting over something.
Isn't that constant?
Not always, no.
You'd think it's constant.
It happens, but it's not all the time. Okay, we're not going to have time to get into all of these cases. Probably we're just going to have time to do one. We'll probably get into this tomorrow. Okay, so the first thing we're going to talk about is what happens when two secant lines intersect inside the circle. Could a secant and a tangent ever intersect inside the circle?
No.
No, a secant and
It's outside or on.
a tangent doesn't enter the circle. It doesn't go inside. So only two secants could meet inside the circle. Okay, or chords, but chords are
Secant.
chords are parts of secants, so that's okay. So we're just going to call them secants. So when two secants meet inside, you get an angle here, angle 1, and the theorem here, 1211, is going to say that that angle has to be the average of the intercepted arcs. That's how I see this. Half the sum is the average of these two arcs. Okay? So how would we prove that? I'm going to give you an auxiliary, because there's an auxiliary, I'm going to give you a hint, but I'm going to give you 2 minutes to think of how you might prove that if you have that situation. Here it's two chords, but imagine that they are secant. Angle 1 has to be the average of arc AB and arc CD. They're suggesting you draw this auxiliary red dotted line, segment, chord. Okay, see if with that, you're able to prove that angle 1, the measure, has to be the average of these two arcs. Try that now, 2 minutes, go.
I think I got it. It's pretty easy.
Good.
Me too.
Start posting it in the chat. Yeah, Mitchell made an argument, but how do you know that those arcs are the arcs of a circle?
Yeah, I thought about that after I sent that. Yeah, it's a circular argument then.
No pun intended. All right.
Actually, I think he intended to make that pun.
Pun intended. Well, you have to ask.
That's a pun in itself. Pun intended, unintended?
Pun inscribed? No, sorry.
Punnett square.
I'm gonna stop.
There's your favorite. The circle's called O, circle O, that you don't like. Okay, we're proving that this is the average of those.
We don't need the center. Vertical angles.
You're proving which one is the average of which.
The point of me drawing the center is to show you that
Oh, they're not on
yeah.
it.
they're not on it. They don't necessarily. They don't have to be on it.
Vertical angles, those two angles are both angle 1, which means the arcs are congruent.
I don't need that. I just need that. Let's see. Oh, it's been 2 minutes. Okay, so here we go. I'm going to label this 2 and 3. Okay, the measure of angle 2 is equal to half the intercepted arc here. So half of arc CD, half the measure of arc CD. The measure of angle 3 intercepts this arc. So the measure of angle 3 is half the measure of arc AB. Right? Because you have this inscribed angle and this arc. You have this inscribed angle and that arc. Okay? By the triangle exterior angles theorem, angle 1 is equal to the measure of angle 2 plus the measure of angle 3. Okay, 1 being the exterior angle, it's equal to the sum of those two, remote
Oh
interior.
yeah, measure of CD plus measure of AB over 2.
Give me a sec. So the measure of angle 1 is equal to, now substitute, instead of angle 2, put half the measure of arc CD. And then for measure of angle 3, put half the measure of arc AB. And then factor out a 1/2. Once you factor out a 1/2, what's left is the measure of CD plus the measure of arc AB.
You can do the problem without auxiliary segment AD. With vertical angles, you can prove that the arcs are congruent. Therefore, an angle 1 is the measure of one of the arcs.
No. These angles are not inscribed. This angle is not related to that arc the way you're saying. It's not inscribed.
Oh, right. But the arcs are still... Okay.
Right? So we draw the auxiliary segment so that we can get this inscribed angle and that inscribed angle. Okay, that's what we're doing. All right, and then this inscribed angle over here is going to relate to this arc. All right, and then the other inscribed angle, 2, is going to relate to this arc. And if you notice, these two arcs, brown and blue, are made by the crossing of these secant lines inside the circle, forming that angle 1. So now we can make a relationship between 1 and these two intercepted arcs. It's the average of the two arcs. Okay, so that gives you the ability to find that. That's a new tool to use to find angles that aren't using the center, angles that are not inscribed, right? We're finding new ways to figure out what angles have to be. And the more tools that we have, the more problems that we can solve in the sciences. This chapter is really more for the sciences. Some other chapters, the type of thinking can be applied to anything, the logical thinking throughout the whole course. But specifically, there's a lot of application for this chapter in engineering. Okay, so that being said, tomorrow we're going to go do this second case. What happens when two secants meet, but they don't meet until they get outside the circle? And so angle 1 is now out there. What happens when a tangent and a secant meet outside the circle? And then how is 1, now we kind of have what's going to happen here.
Equivalent.
Right? 1, if I were to take this point of tangency and this point of tangency and connect it to the center,
and the supplementary.
We know that the central angle and 1 we already showed are supplementary, but the central angle and y are the same. So we know that these are going to end up being supplementary. Okay?
I don't think we have time for that though.
I know, but what about here? What is 1 in these going to be? And what is 1 in these going to be? It's saying that it's going to be this. Half the difference of x and y. Half the difference of x and y. Okay, so we're going to have to prove that, and we can open that up to start. We're going to start here tomorrow. So if you want to work on that and try to figure that out yourself, you're welcome to do that. There's no additional homework for you. And you
second case. Oh, right. Half the difference.
George Smith, and I am now on office hours for you. Thank you.
Bye.
Thank you, Mr. Rosenthal.
Gracias.
De nada.
Thank you, Mr. Rosenthal.
You're welcome.
Mr. Rosenthal.
Mm-hmm.
I got an incomplete for the test, and I don't know why. Why is that? Do I have to discuss it with you?
Who is this talking to me?
Cayman.
It's related to our past conversation.
Okay.
Okay, it's just a way for me to know that you know it, to validate it.
Okay. Okay.
Yeah. So you'll just we'll set that up. I'm gonna have the retake makeup figured out sometime this week or on the weekend, so that everybody will know what the plan is by next week, hopefully.
Okay. But I broke my thumb, so like, is there a way like I could just take it like? Oh, my handwriting's gonna be like really messy, I think.
Okay.
Okay. Is
Yeah,
there a way I could take it
I don't
online?
know how to get around that other than you just have to do the best you can.
Okay.
Yeah,
Thank
can you
you.
see me? Is your thumb up like this in a splint?
Yes. Like,
Okay, so you'll have to grab the pencil like this and write like that.
okay.
Okay, it won't be nice, but it should be legible.
Okay.
Okay?
Thank you, Mr. Rosenthal.
You bet. Feel free to ask me questions. Luca, were you going to stay on and ask me the canoe problem and some other of the problems?
Mr. Rosenthal?
Mm-hmm.
Yeah, can you help me with the canoe problem?
The canoe?
Yeah.
Okay, yeah. Do you have it in front of you? Is there a way for you to share that in your screen so I can?
Yeah, it's around. Can I go get it? 1 second.
Yeah, or just read me the problem because I don't have it in front of me.
All right, cool. 1 second.
If anybody's sticking around, I'm going to do that canoe problem with the vectors. Anybody else have a question while we're waiting? Max, any questions? Celine, Mark, Mitchell, Surin, Andrew, any questions?
Thank you, Mr. Rosenthal. Have a good day. See you tomorrow.
You betcha. Max, Celine? No, okay. Andrew, Mitchell? Bye. Bye. Andrew, any questions?
All right, I have it.
Okay, go ahead.
All right. So a canoe's heading 40 degrees south of east.
Okay, give me a sec. 40 degrees south of east.
Yeah.
So here's east. Okay, here's south.
Okay.
40 degrees is going to be like that.
Yeah.
In that direction, right?
Yeah.
Okay, go ahead.
All right. Is being paddled at a rate of 10 miles per hour.
That's the magnitude of the vector.
Yeah.
There you go.
The current is pushing the canoe 25 degrees west of north.
Okay, let's do that. Here's north, and here's west. West of north, and how many degrees?
25 degrees.
Okay, so here we go. We have 25 degrees is here because we're going west from the north line.
Yeah.
Okay, and at what mile per hour?
4 miles per hour.
4 miles per hour. So you get these two vectors now. Okay, we want to know the result of that, right?
Yeah.
Okay, so the first step is we're going to need to get these into vector coordinates. So we're going to want to know what this point, where that point would be on a coordinate plane would give me the vector coordinates, because that's going to, this magnitude is a hypotenuse to a right triangle that we like to draw it to our x-axis here. Okay, so if you have a little right triangle there and you already have the 10 miles per hour with the 40 degrees, all right? So how are we going to get that? What is this distance? If you already know the magnitude of the vector, what did we say is this component here? Think trigonometry.
If that's the distance, then
Here's your angle is right here. What is this side? Is that opposite, adjacent, or hypotenuse? This side.
Oh, that's adjacent.
Adjacent. What is your known information?
10.
But is that opposite or hypotenuse?
Hypotenuse.
Okay, so you have adjacent and hypotenuse. What trig function are you thinking of? or ratio?
Cosine, right?
That's right. So when you already have the magnitude, that magnitude gets multiplied to your cosine. So this is 10 cosine of 40 degrees.
Yeah.
All right, what's this vertical distance then?
That
Opposite the 40 degrees, right?
Yeah.
And then the hypotenuse.
Yeah.
So that's 10 what?
That's 10 sine, right?
Yes, 10 sine of 40. Now, the one problem with that is that this is in quadrant 4.
Yeah, so wouldn't it be negative 10?
Correct. Okay, so positive for the x, negative for the y. The only other way to do that is to do the full angle that is from 0 moving this way. How many degrees till you get to there? Well, you can subtract it from 360, right? This 40 degrees.
Yeah, so 320.
So if I did 10 sine of 320, I would not need to put the negative.
Yeah.
It would know. But my calculator doesn't know that the 40 degrees is below. The calculator thinks that this is happening in quadrant 1, 40 degrees up here.
Yeah.
So we have to put the negative in. Or if you don't want to do that, you can choose to call that 320 degrees instead. Okay,
Yeah.
and then you could put 320 there also, but that won't change that because the calculator knows that 320 is in quadrant 4.
Yeah, and that would still be positive.
Exactly.
All right,
You
so
get
now
that?
we have to do that.
So now as a vector coordinate, you now have your x and y.
Yeah.
X is 10
10
sine 40. Y, your y component is negative 10 sine of 40. Okay, now we're going to do the same thing with the current vector. Now, I want to draw it. Now, this is not drawn to scale. I'm going to make the vector appear longer, but it's supposed to be shorter than that one. But 4 miles per hour is less than 10. But I'm only doing it so you can see. Instead of drawing it to the y-axis, which you can do, but it's going to mess up your sine and cosine. If you want to keep cosine as your x and sine as your y, draw it to the x-axis. But then what's this angle? Is not 25 anymore. So this is 4 miles per hour. What's this angle here?
That's 25.
No, this one is 25.
Oh.
And you can see that can mess up your entire problem, right?
Yeah.
Okay.
So it'd be 65.
Correct. Okay. Now again, your calculator thinks 65 degrees is over here.
In quadrant 1.
Right? So you could do 180 minus 65 would be 115. Your calculator would then know that 115 is over here. Or you can take responsibility for putting the negatives and positives in. Okay, yeah. This is quadrant 2, so your x is going to come to the left, your y is going to go up. So your x is going to be negative. You can even put it in now. Your y is going to be positive. Right?
Yeah.
Okay, again, this, because I drew this to the x-axis, your x is the adjacent side. So it's going to be cosine. And you have your magnitude of 4, your multiplier. So 4 cosine 65, and it's going to be negative. Then you're going to come up. So that's positive. 4 is your multiplier. Sine of 65 degrees. And you could just fill that in. Negative 4 cosine, 4 sine.
Yeah.
So really, we need to add these up.
Yeah, so you find the results of both, and then you add the x's and you add the y's.
Yeah, exactly. So let's go ahead and do that now.
Okay.
So I have cosine of 40 times 10, 7.66 about.
Yeah, and then negative sine of 40 is negative 6.43.
Okay.
And then negative 4 cosine of 60 would be negative 1.69.
Okay, cosine of 65, I'm just going to do that in there, times 4. Negative 1.69 here.
Yeah. And then 4 times sine of 65 would be 3.63.
3.63, exactly. And then you add these up. So 3.63 minus 6.43 is going to give me this resultant. That gives me here negative 2.8, 2.80.
Oh,
Okay. When I add these together, 7.66 minus 1.69, I get 5.97.
Mm.
Okay, so sketch that. What does that look like if I were to sketch that out? Okay, so here's my north-south again.
it's going to end up being in quadrant 4 again.
Positive, negative, yeah. And that makes sense because the magnitude of this one was 2.5 times the magnitude. So it's going to have more of an effect on the canoe than the current, which means the canoe is going to cheat more towards what this vector is doing to the canoe. Okay, so it makes sense. Okay, so 5.97 is longer this way than it is down. So maybe put a point, you know, and you're just estimating.
Yeah.
So you have this, that's what your result, that's where the canoe is going to end up going. So it's going to end up being, this current's going to make the canoe change to there instead, right?
Yeah.
Okay, good. Now you're getting a picture. All right, so but what I don't have is that angle, and I do not have the magnitude. This time I have this.
We have two sides though, so we can use Pythagorean theorem.
Yeah, and this is 2.8. So 5.97
plus
squared,
2.8 squared
and then
equals
you
c squared.
and take the square root, and that'll be your magnitude. So I'll do that. Squared plus 2.8 squared.
I get it around 25.
And take the square root. Did you take the square root?
Oh, no.
What'd you get?
Oh, I don't have a calculator near me, so I'm just.
I got, okay, let's do 5.97 squared plus 2.8 squared is 43.4809.
Okay.
Then I take the square root and I get 6.59. So,
all right.
So we're going to round that to 6.6. And what does that mean? What is that number?
Oh, that's the magnitude, right?
All right. And so what would that mean for our canoe?
Oh, it's direction?
It's got a magnitude. So what is that for the canoe? The 6.6 is the direction of the canoe? That would be the angle would tell you the direction.
Yes.
The
so
magnitude is
the speed, right?
Yeah, it's the speed, not the velocity.
Yeah.
Speed, because without the direction, you don't have a velocity. So this is just the magnitude. So it's just the speed component. So that's how many miles per hour. So that current slowed us down, didn't it?
Yeah.
Yeah, that current slowed us down because some of that 4 miles per hour was working against our 10 miles per hour. And if you look at it, it's almost directly the opposite direction. If that were exactly the opposite direction, that 4 miles per hour would just be simply taken away from the 10. It would just be 10 minus 4, like a number line, right?
Yeah.
If you add negative 4 in the other direction, it would just take 4 from the 10. But it wasn't exactly in the opposite. And that's the beauty of what we're learning right now, is that you don't have to do this along a single number line. We can do it off the number line. Okay, and finally, let's get this angle. How am I going to get that angle?
We can do any of them, right? We can do cosine,
yeah.
sine, or tangent.
So let's do, you pick.
All right, let's do tangent then.
Tangent of the angle is the ratio 2.8 to 5.97. So inverse tangent of the ratio gives you the angle. So I will simply put this into my calculator, 2.8 divided by 5.97. So you've already gotten to the easy part now. This, you've already done the hard part.
It's just calculator work now.
Yes, exactly. And then inverse tangent, it's about 25 degrees. So this is about, theta is about 25 degrees, and this direction is south of east. Now we have a velocity that we can describe. We are going 6.6 miles, the canoe is going to end up going 6.6 miles per hour at 25 degrees south of east. And that does it.
All right. Thank you very much.
Got it, Luca. All right. So some problems I can message you, but
Yeah.
problems like this would be a disaster trying to message you. So that's
Yeah.
why, yeah. Okay.
Okay. I'll see you tomorrow at the lesson.
You bet. Good job.
All right. Thank you.
All right. Bye.
Bye.